I want to start today with a question that I think about more than most doctors probably admit to. How many decisions do you make every single week? Automatic decisions, habitual decisions, the kind you do not even register as decisions anymore, that are quietly working against you? Not dramatically, not in a way that sends you to the emergency room, but in a slow, cumulative, invisible way that your body is absorbing year after year without ever sending you a clear signal to stop. I am not talking about the obvious ones. You already know about smoking, you already know about sitting too much and eating too much sugar and not sleeping enough. Those conversations have been had. What I am talking about today is something different. Something that happens inside most kitchens, in most households, several times a week, performed by people who are actively trying to do the right thing, trying to save money, reduce waste, cook at home instead of ordering out, and who have never once been told that 5 specific foods they regularly reheat carry real, documented, science-backed concerns that deserve their attention. My name is Dr. Adam, and I have spent over 2 decades in internal medicine and nutritional health, and the most consistent pattern I have noticed across thousands of patient conversations is not what people are doing wrong out of laziness or ignorance. It is what they are doing wrong out of genuine effort. People who are trying. People who cook at home. People who batch cook on Sundays and eat leftovers through the week because they are being practical. This video is for those people, because you deserve to have accurate information about what is actually happening inside those containers in your refrigerator. I am going to walk you through 5 specific foods today. For each one, I will tell you exactly what happens chemically or microbiologically when heat touches them a second time. I will be very honest with you about the strength of the scientific evidence, because responsible health communication means telling you not just what the risk is, but how certain we are about it. Some of what I share today is established beyond reasonable scientific doubt. Some of it is genuinely concerning based on current evidence, with ongoing research adding more detail. I will tell you the difference clearly for each food. And for every single one of them, I will give you a practical, simple alternative that costs you nothing and eliminates the concern entirely. Are you ready? Let us get into it. Food 1. Fried foods reheated in oil. The chemistry happening inside your pan, and why the evidence is stronger than most people realize. Picture this. You made fried chicken on Monday night. There is half a portion left. You covered it and put it in the fridge. Tuesday afternoon, you take it out, heat a little fresh oil in a pan, put the chicken in, and 3 minutes later, you have crispy, hot leftovers that taste almost exactly as good as they did the night before. You feel good. You saved the food. You did not waste anything. And here's what most people never learn. At the exact moment that fresh oil hit the heat, a chemical process began inside your pan that has been the subject of serious, peer-reviewed scientific attention for over 30 years. A process that generates compounds your body absorbs, and that researchers across Europe, Asia, North America, and Australia have consistently flagged as a genuine health concern. Let me walk you through the chemistry slowly and clearly, because once you understand it, you cannot unsee it. The cooking oils that most households keep on their shelves, sunflower oil, corn oil, soybean oil, standard vegetable oil, are rich in what nutritional science calls polyunsaturated fatty acids. You have probably seen that term on food labels. What it means in practical terms is that these oils have a molecular structure that is inherently unstable under high heat. When you heat them to frying temperatures, their molecular chains begin to break apart through a process called oxidative degradation. Now here's the critical part. When you take food that has already been fried, food whose surface is already coated in residual oil that has already been heated once, and you apply heat again, either by adding fresh oil or by reheating in the same oil, you are taking a product that is already in a partially degraded state and pushing it further down the oxidation pathway. That process generates a class of chemical compounds called lipid oxidation products. The ones that have received the most scientific attention are toxic aldehydes, and specifically 2 compounds with names most people will never encounter in daily life: 4-hydroxynonenal, which scientists abbreviate as 4-HNE, and malondialdehyde, abbreviated MDA. These are not obscure laboratory curiosities. They are compounds that your body actually absorbs when you eat food cooked in thermally stressed polyunsaturated oils. A comprehensive review published in Frontiers in Nutrition in 2021, led by researcher Martin Grootveld and drawing on decades of accumulated evidence, confirmed that heating polyunsaturated fatty acid-rich culinary oils to standard frying temperatures generates these aldehydes in measurable quantities, and that following ingestion, these aldehydes are absorbed from the gut directly into the systemic circulation. The research reaching this conclusion comes from laboratories in the Americas, Europe, Australasia, Asia, and Africa. This is not a fringe finding, it is a well-replicated result. What do these aldehydes do once they are inside you? At the cellular level, research published in Food Chemistry and reviewed extensively in the scientific literature describes aldehydes like 4-HNE as capable of inducing what scientists call conformational changes in enzymes, meaning they alter the shape and function of the proteins your cells depend on. They form what are called protein adducts, essentially binding to proteins and interfering with their normal operation. They activate pro-inflammatory pathways, and they contribute to what biologists call oxidative stress, which is an imbalance between the damage accumulating inside your cells and your body's capacity to neutralize and repair it. DNA fragmentation and necrosis, the death of cells, have both been documented in research examining high-dose aldehyde exposure. Now, I want to be precise here, because precision is what separates responsible science communication from fear-based health content. The evidence that these aldehydes are toxic at high doses in laboratory conditions is robust. The evidence that chronic exposure to oxidized cooking oil is associated with inflammatory pathways and cellular damage is well established across multiple research groups and methodologies. What the human epidemiological literature is more cautious about is drawing a direct causal line between reheating fried food twice a week in a home kitchen and a specific disease outcome. Human studies are complicated by the enormous number of variables in a person's diet and lifestyle, and responsible scientists acknowledge that complexity. What can be said with genuine confidence is this: chronic oxidative stress and chronic low-grade inflammation are both well-documented contributors to the conditions that precede serious disease, including various cancers. Repeated exposure to aldehyde-generating cooking practices is a documented contributor to oxidative stress. That chain of reasoning is grounded in the literature. There is also something most people are never told about the type of oil they use. Not all cooking oils behave equally under heat. Oils rich in polyunsaturated fats, sunflower, corn, and soybean, generate significantly more toxic aldehydes during frying than oils with higher proportions of monounsaturated or saturated fats. Extra virgin olive oil, with its high oleic acid content and natural antioxidant compounds called polyphenols, performs substantially better under frying conditions and generates far fewer aldehydes. Avocado oil and refined coconut oil are also more heat stable. A study highlighted in the British Medical Journal in 2015 specifically flagged the aldehyde generation problem in polyunsaturated oils and suggested that home cooks consider more heat-stable alternatives for frying. What to do differently, starting tonight. First, never reheat already fried food in oil. Not fresh oil, not the same oil. Never. The combination of previously cooked food with a second round of high-heat polyunsaturated oil generates significantly more chemical load than the original cooking event. Instead, use a dry oven at 180 degrees Celsius or an air fryer. Both methods restore texture effectively without adding a single molecule of new aldehyde exposure. Second, treat frying oil as single use. The moment polyunsaturated cooking oil has been brought to frying temperature once, its oxidative stability is already compromised. Reusing that same oil for a second frying session substantially increases the aldehyde content of everything you cook in it. Discard it after one use. Third, and this is a long-term change worth making, consider switching your everyday cooking oil. Extra virgin olive oil, avocado oil, and refined coconut oil are all significantly more heat-stable than sunflower or corn oil. This is a change that costs you almost nothing and reduces your aldehyde exposure every time you cook. Food 2. Leafy greens, spinach, kale, chard, and arugula. The nitrogen chemistry that happens in your refrigerator overnight. This one surprises people more than almost anything else I talk about, because it involves a food that every doctor, every dietitian, every nutritional researcher agrees you should eat more of. And they are right. The nutritional case for leafy greens is genuinely overwhelming. Vitamins A, C, and K, folate, iron, magnesium, fiber, antioxidants, cardiovascular benefits. I am not here to tell you to eat less spinach. I am here to tell you something very specific about what happens when you cook it, store it, and then apply heat to it a second time. Here is the chemistry. All leafy greens are naturally high in nitrates. This is not a problem. In fact, dietary nitrates from vegetables are well studied for their health benefits, including their role in supporting cardiovascular function and lowering blood pressure. When you eat fresh spinach or kale, those nitrates move through your system in largely their natural form. But when you cook leafy greens, the cellular structure of the leaves breaks down. This releases nitrates into a warm, moist environment where bacteria that are naturally present in the food begin converting them into a related compound called nitrites. This conversion process occurs during cooking and continues during storage, even in your refrigerator, just more slowly. The longer cooked greens sit, whether on the counter or in cold storage, the more nitrite accumulates. Then comes the second heat event. When you put that stored cooked spinach in the microwave or back in the pan to warm it up, those nitrites undergo another transformation. Under heat, in the presence of amino acids, which are present in the food, nitrites can react to form compounds called nitrosamines. The International Agency for Research on Cancer classifies certain nitrosamines as probable human carcinogens. That classification, which falls in their Group 2A category, is based on consistent and reproducible evidence from animal studies showing tumor formation and on epidemiological data in humans suggesting associations between high dietary nitrosamine exposure and certain cancer types, particularly colorectal, gastric, and esophageal cancers. Work published in The Lancet Oncology has examined these associations in detail. Now here is where I will do what I promised. Be very precise about the strength of the evidence. For healthy adults who are properly refrigerating their cooked greens and reheating them once, the nitrosamine levels formed during normal household food preparation are, according to current food safety research, well below established toxicological thresholds. The European Food Information Council, which previously issued a broad caution against reheating spinach at all, subsequently reviewed the available evidence and updated its guidance. It acknowledged that with proper cold storage and a single reheating, the nitrite levels produced are far below any concentration associated with documented harm in healthy adults. The concern rises meaningfully under specific conditions. When cooked greens are left at room temperature for extended periods before refrigeration, which allows bacteria to work faster and longer. When food is reheated multiple times, since each additional heat cycle creates additional opportunity for nitrosamine formation. And for particular vulnerable populations, infants, pregnant women, individuals with compromised immune systems, where even lower level exposure warrants greater caution. The reason to build better habits in this area is not immediate danger from a single reheated bowl of spinach. It is the cumulative picture across repeated exposures over months and years, and the fact that the alternatives are so easy and nutritionally complete that there is genuinely no good reason not to make the change. What to do differently? Starting tonight. The simplest and most effective change is to eat your cooked, leafy greens cold. Cold cooked spinach dressed with lemon juice and olive oil in a grain bowl. Wilted kale folded into a wrap with tahini and roasted vegetables. Cooled chard tossed through a salad with toasted nuts and vinaigrette. Every nutrient remains fully intact. The nitrosamine formation pathway is not activated because there is no second heat event. Cold cooked greens are genuinely underrated. Most people who try them find the texture and flavor entirely satisfying. If you prefer them warm, the most effective solution is to cook only the portion you are eating right now. Not a batch for the week, just tonight's serving. This eliminates the storage and reheat cycle entirely. If you do have leftover cooked greens, refrigerate them promptly. Within 2 hours of cooking, reheat once only to at least 70 degrees Celsius throughout. Then eat them completely. Do not reheat them a second time. Each additional heating cycle increases nitrosamine formation in a way that compounds rather than adding linearly. If you are cooking for infants or young children, the guidance here is more conservative. Serve cooked leafy greens fresh. Do not reheat them for young children. Their developing systems handle nitrite exposure with less tolerance than healthy adults. Food 3. Cooked rice. The one reheating risk with the strongest, most direct, most universally agreed upon evidence. I want to open this section with a statement that carries no ambiguity, no hedging, and no complexity. What I am about to describe is the most thoroughly documented, most consistently confirmed, most universally recognized food safety hazard of anything on this list. This is not about long-term accumulation of trace chemical compounds. This is not about epidemiological data with complex variables. This is about a specific bacterium, specific toxins it produces, and the very specific way that cooked rice creates ideal conditions for both, conditions that a microwave cannot fully reverse. Every major food safety authority in the world, the UK Food Standards Agency, the United States Food and Drug Administration, the World Health Organization, Food Standards Australia, New Zealand, issues explicit guidance about rice handling and reheating. This is not precautionary language based on theoretical concerns. It is based on decades of documented outbreaks, clearly understood microbiology, and a mechanism of harm that has been confirmed repeatedly in controlled research. Here is exactly what happens, step by step. Raw rice from any supermarket, anywhere in the world, naturally carries dormant spores of a bacterium called Bacillus cereus. This is not contamination in the way we usually think about contamination. It is simply a natural feature of this grain in its raw state. These spores are extraordinarily resilient. Boiling water cannot destroy them. Standard cooking temperatures, including the full rolling boil required to cook rice properly, cannot touch them. They survive the cooking process entirely intact, sitting dormant inside your perfectly cooked, perfectly good-looking, perfectly normal-smelling rice. The moment that rice begins to cool, the situation changes entirely. As the temperature drops from boiling toward room temperature, it passes through a range that microbiologists call the temperature danger zone, approximately 8 to 60 degrees Celsius. This is the range where Bacillus cereus spores do not just survive. They activate, germinate, and begin multiplying rapidly. And critically, this is the exact temperature range that cooked rice passes through as it cools on your counter, in your pot, or in a container with the lid on. All conditions that slow the cooling process and extend the time the rice spends in that zone. While Bacillus cereus multiplies, it produces toxins. Two are particularly significant: an emetic toxin that causes vomiting, and a diarrheal toxin that produces exactly what the name describes. The emetic toxin is what makes improperly handled rice specifically dangerous in a way that surprises most people. It is heat stable. It survives reheating. When you put that rice in the microwave the next day, you eliminate the live bacteria. But the toxin those bacteria already produced during the cooling and storage period, your microwave cannot touch it. It remains intact inside the food and enters your body in full biological activity. Let that sink in for a moment. The reheating you believe is making the food safe is not neutralizing the hazard if the toxin was produced before you ever touch the microwave button. Symptoms of Bacillus cereus food poisoning typically begin between 1 and 6 hours after consuming contaminated rice. The emetic form produces sudden, acute nausea and vomiting. The diarrheal form produces cramping and prolonged gastrointestinal illness that can last anywhere from 24 hours to several days. For most healthy adults, it is a deeply unpleasant experience. For elderly individuals, very young children, pregnant women, and people on immunosuppressant medications, it can escalate to serious illness requiring medical attention. This is not rare. Bacillus cereus is one of the most common causes of food-related illness traced to individual food items in both restaurant and home settings globally. The UK's National Health Service specifically names it in its public food safety guidance. Outbreaks are reported to public health authorities regularly and are almost always traced back to the same combination of factors: cooked rice, cooled slowly, stored too long, and then reheated. Now, I want to mention something that rarely gets discussed in standard food safety messaging: the dramatic acute food poisoning event, the one that puts you in bed for a day and a half, is not the only way this organism affects you. There is also what researchers describe as low-level chronic exposure. Episodes where the toxin load is not large enough to cause unmistakable food poisoning, but where your gut and immune system are nonetheless responding to a foreign insult repeatedly. Gut inflammation caused by repeated low-level bacterial toxin exposure has documented connections to longer-term digestive health outcomes. The science on exactly how those connections play out is still developing, but the basic relationship between chronic gut inflammation and downstream systemic health effects is well established. The single most important change is cooling speed. Cool cooked rice within 1 hour of finishing cooking. The practical technique is to spread it across a wide, shallow container rather than piling it deep in a bowl or leaving it in the cooking pot. A greater surface area means heat escapes faster, which means the rice spends less time in the bacterial danger zone. This one habit change eliminates the vast majority of the risk. Refrigerate it promptly and eat it within 24 hours. The longer cooked rice sits in the refrigerator, the more opportunity Bacillus cereus has had to work. Even cold temperatures only slow the process, they do not stop it entirely. When reheating, heat it completely, all the way through until it is uniformly steaming hot, not just warm on the outside. Then eat it completely in that meal. Do not put it back in the refrigerator after reheating. Once is acceptable under the right conditions. Multiple reheats of the same batch are where the risk becomes genuinely significant. Be especially careful with rice that has been sitting in a warm kitchen, a pot left on the counter while you got distracted, a serving dish sitting out at a gathering, a container that was not refrigerated until hours after cooking. If cooked rice has been at room temperature for more than 2 hours, every food safety authority in the world gives the same guidance. Discard it. The cost of the rice is not worth the risk. Food 4. Chicken and poultry. Why the outside temperature of your reheated chicken tells you almost nothing about the inside. This one is, at its core, a problem of physics. And once you understand the physics clearly, you will never again touch the outside of a microwaved piece of chicken and assume the interior is safe. Let me walk you through the exact scenario that plays out in millions of kitchens every day. You cooked roasted chicken thighs last night. They were fully cooked, internal temperature reached, exterior golden and crisp, absolutely fine to eat. You put the leftovers in a container and refrigerated them. Today at lunch, you take 2 pieces out, put them on a plate, slide the plate into the microwave, and heat for 2 to 3 minutes. You press the outside of the chicken with your finger. It is hot. You eat it. That is a completely normal Tuesday in an enormous number of households. And the problem lives in one specific step of that process, the moment you touched the outside and made a judgment about what was happening on the inside. A microwave oven does not heat food the way a conventional oven does. A conventional oven uses hot circulating air that envelops the food and gradually penetrates from the outside inward, raising the temperature of the entire piece relatively uniformly over time. A microwave works by emitting electromagnetic radiation that excites water molecules within the food itself to generate heat internally. This is why microwave cooking is faster. It is generating heat throughout the food, not just at the surface. But here's the physics problem. Different parts of the same piece of chicken have dramatically different water content, fat distribution, and tissue density. Areas with higher water content respond to microwave energy rapidly and reach high temperatures quickly. Areas with lower water content, or higher fat content, or different tissue structure absorb that microwave energy at a completely different rate. The result is what food scientists call cold spots. Areas within the food that never reach the temperature the outside does. Cold spots are invisible. You cannot see them, smell them, or identify them by touch. The exterior of a chicken thigh can reach temperatures that would kill any bacteria present, while a cold spot 3 centimeters toward the center sits at a temperature where bacteria are not being killed, where they are, in fact, multiplying. Now, which bacteria are specifically relevant to poultry? Salmonella and Campylobacter are both extensively documented in chicken. Campylobacter is the most commonly reported foodborne bacterial pathogen in many high-income countries, and poultry is the primary transmission source. Salmonella causes over 1 million illnesses in the United States alone every year, according to CDC data, with tens of thousands of hospitalizations. Both organisms require the same thing to eliminate them: sustained internal temperatures at or above 75 degrees Celsius throughout the entire piece of food. If reheating produces cold spots that never approach that threshold, you are not making the food safe. You are making some parts of it hot while leaving bacterial reservoirs intact in others. Proper initial cooking eliminates these organisms when done correctly. But handling after cooking, your hands, utensils, cutting boards, surfaces, creates ongoing recontamination risk. A piece of chicken that was perfectly safe when it came out of the oven on Monday can pick up new contamination before it goes into the refrigerator. And if Tuesday's microwave reheating creates cold spots, that contamination survives. Salmonella infection means fever, often significant fever, combined with severe abdominal cramping, nausea, vomiting, and diarrhea that can persist for a week or more. It is a full systemic immune event. Campylobacter produces a similar picture. Both can, in vulnerable individuals, lead to bloodstream infections, reactive arthritis, and serious complications that extend well beyond the initial gastrointestinal episode. I also want to mention something that sits just below the level of obvious food poisoning: repeated low-level bacterial exposures, too small to produce the classic unmistakable symptoms, but real enough that your immune system is continuously responding, have been studied in connection with chronic low-grade gut inflammation. These are exposures that can manifest as intermittent stomach aches, fatigue after meals, or digestive discomfort that you have been attributing to other things. The relationship between repeated subclinical pathogen exposure and sustained gut inflammatory responses is a genuine area of active research. What to do differently? Starting tonight. The most reliable reheating method for chicken is a conventional oven. Place the pieces in a baking dish, cover the dish tightly with aluminum foil. The trapped moisture creates a steaming effect that penetrates every part of the food uniformly, and heat at 175 degrees Celsius for 15 to 20 minutes. This method eliminates cold spots, ensures uniform safe temperature throughout, and as a bonus, preserves far more moisture than a microwave. The chicken tastes better this way. If a microwave is your only option, change how you use it. Begin by cutting the chicken into small, evenly sized pieces. Smaller pieces dramatically reduce the thermal distance between the surface and the center. Use medium power rather than maximum. Lower power allows the microwave energy to distribute more gradually and reduces the temperature differential between different parts of the food. Stop the microwave halfway through the cooking time and rearrange or flip every piece, moving outer pieces to the center and center pieces outward. Then, after the microwave stops, leave the food covered for a full 2 minutes. During that rest period, heat continues to conduct through the food and cold spots equilibrate toward the surrounding temperature. A food thermometer inserted into the thickest part of the largest piece should read 75 degrees Celsius before you eat. Alternatively, and this may sound simple because it is, consider eating cold chicken. Cold shredded chicken in a salad, in a wrap, over rice noodles, in a sandwich. This is not a compromise or a lesser meal. It eliminates every risk discussed in this section completely. Zero reheating, zero cold spots, zero bacterial concern. Food 5. Cooked potatoes. Two completely separate chemical stories happening simultaneously in the same bowl of leftovers, potatoes are the most universally reheated food in most households. Roasted potatoes, mashed potatoes, boiled potatoes, jacket potatoes, leftover portions are almost a daily reality in kitchens around the world. And the science of what happens when you reheat them involves not one, but two entirely independent phenomena, operating through completely different mechanisms, both worth understanding clearly. Let me walk you through both. The first story, acrylamide. When starchy foods like potatoes are cooked at temperatures above 120 degrees Celsius, which describes virtually any roasting, frying, or high-heat baking, a chemical compound called acrylamide forms as a byproduct of the Maillard reaction. The Maillard reaction is the same chemical process responsible for the golden brown color and rich flavor of roasted and fried food. The crispy edges on your roasted potatoes, the browning on toasted bread, the color of baked chips, all of that is the Maillard reaction, and acrylamide is produced alongside it through the interaction of reducing sugars and an amino acid called asparagine, both of which are naturally present in starchy foods. The International Agency for Research on Cancer classifies acrylamide as a probable human carcinogen. A potato is cooked once and then cooled and refrigerated. Physical and chemical changes occur at the surface. The surface dries out, reducing sugars and free asparagine. Precisely the two compounds that react to form acrylamide under high heat, Na, concentrate at that dried surface in greater proportions than they were present during the first cooking. When you then apply high heat a second time, those concentrated precursors drive the acrylamide forming reaction more favorably than the first cooking did. The European Food Safety Authority, which has conducted extensive evaluation of acrylamide in food, has specifically identified the reheating of already cooked high-starch foods as a practice that can increase acrylamide formation beyond what occurred during initial cooking. Combined with the oil oxidation hazard from food one, which is also maximized when you refry already cooked potatoes, reheated potatoes represent the stacking of two separate chemical concerns in a single dish. The EFSA's guidance on reducing acrylamide exposure includes cooking starchy foods to the lowest temperature that achieves the desired result, avoiding dark browning, and, this one surprises most people, not storing raw potatoes in the refrigerator before cooking. Cold storage increases the concentration of free sugars in raw potatoes, which means more acrylamide forms during the very first cooking event. The second story, resistant starch, and why reheating destroys something genuinely beneficial. This second story is less about adding risk and more about eliminating a nutritional benefit that most people have never been told exists, and that they are accidentally destroying every time they apply high heat to already cooked potatoes. When potatoes are cooked and then cooled completely in the refrigerator, a fascinating transformation occurs at the molecular level. A portion of the regular digestible starch in the potato undergoes a structural rearrangement called retrogradation. During this process, the starch molecules reorganize into a form that the digestive enzymes in your small intestine cannot readily break down. Nutritional scientists call this resistant starch, resistant because it resists digestion in the small intestine. Resistant starch has been studied extensively for its genuine health benefits. Research published in the journal Advances in Nutrition and in multiple other peer-reviewed sources has linked higher resistant starch intake to improved insulin sensitivity, lower postprandial blood glucose response, meaning blood sugar rises more slowly and moderately after eating, reduced appetite through extended satiety, and healthier gut microbiome composition, because resistant starch that reaches the large intestine acts as a prebiotic, feeding beneficial bacteria. A cold-cooked potato is metabolically a meaningfully different food than a hot, freshly cooked one. Its glycemic impact is lower, its impact on gut bacteria is more favorable, and its effect on blood sugar is more gradual. The moment you apply high heat to that cold-cooked potato, whether in a microwave, in an oven, or in a frying pan, the retrogradation reverses. The resistant starch converts back into regular, rapidly digested starch. The structural change that happened during cooling is undone in minutes. The glycemic benefit disappears. The prebiotic function is eliminated. What was a gentler, more beneficial food for your metabolic response is now a food that raises blood sugar quickly. Your pancreas responds to rising blood glucose by triggering your beta cells to produce and release insulin. A single rapid blood sugar rise from a reheated potato is not a medical event for a healthy person. But consider the pattern across years of eating. Regular high glycemic load meals, driven in part by consistently destroying the resistant starch in cooked potatoes through reheating. Research on chronic beta cell overwork, in the context of repeatedly elevated glucose demands, shows connections to declining insulin sensitivity and progressive beta cell fatigue. This is a long-term consideration, not an emergency, but it is a real one. And the alternative is so simple it seems almost too easy. What to do differently? Starting tonight. Cold potato salad is one of the most underrated staples in a health-conscious kitchen, and I say that as someone who spent years giving nutrition guidance to patients. A cold cooked potato dressed with extra virgin olive oil, a small amount of apple cider vinegar or lemon juice, fresh herbs, and a little mustard is genuinely delicious. It retains all of the resistant starch. It carries none of the acrylamide concerns associated with a second high heat cooking. It is nutritionally excellent. If you have never tried it, make it this week. If you need your leftover potatoes warm, use the lowest heat that achieves your goal. Steam them gently. Warm them in a low oven covered tightly in foil so the moisture stays in. Aim to take the refrigerator chill off, not to drive a second full Maillard reaction. Warm is the goal. not hot. Never refry already cooked potatoes in polyunsaturated oil. Of everything covered in this video, that specific combination, a second high heat event on already cooked starchy food in oil that is itself being heated for the second time, represents the highest chemical load in a single dish. Maximum acrylamide formation, maximum oil aldehyde generation, minimum resistant starch benefit. There is simply no good reason to do it when the alternatives are this straightforward. And take note of the raw storage point. Keep raw potatoes in a cool, dark, dry place, not the refrigerator. Cold temperatures increase free sugar content in raw potatoes, setting up conditions for greater acrylamide formation even during the very first cooking event. We have now gone through all 5. Before I summarize the practical changes, I want to say something that I think is more important than any individual piece of food science in this video. The way health information is usually delivered to people, through fear, through exaggeration, through absolute causal claims that the actual science does not support, does real damage. It creates anxiety without empowering change. It makes people feel like no matter what they do, they are going to get sick. And when that feeling sets in, a lot of people stop paying attention to any of it, because the noise-to-signal ratio feels impossible to navigate. That is not what I want to leave you with today. Here is what the science actually shows. Each of these 5 foods involves a genuine, documented, well-sourced concern that gives you a real reason to do something slightly differently in your kitchen. None of them is a guarantee of disease. None of them means that everything you have done until now has been irreversibly harmful. The human body is an extraordinarily capable system. Your cells repair themselves continuously. Your liver processes chemical exposures every single day. Your immune system clears damage constantly. The habits described in this video are risks that accumulate over long periods of repeated exposure, which also means that changing those habits starting now is genuinely, biologically meaningful. Let me give you the practical summary you can actually use. For fried food leftovers, reheat in a dry oven at 180 degrees Celsius or in an air fryer, never in oil, never in the same oil, never in fresh oil. Treat frying oil as single use. Consider switching from sunflower and corn oil to extra virgin olive oil or avocado oil for all of your high heat cooking going forward. For cooked leafy greens, eat them cold whenever you can. Cold spinach, cold kale, cold chard in a bowl or salad is nutritionally complete and carries zero concern about nitrosamine formation. If you need them warm, cook only the portion you are eating right now. If you have leftovers, refrigerate within 2 hours, reheat once to 70 degrees Celsius throughout, and then eat them completely. Do not reheat them a second time. For cooked rice, spread it wide and cool it fast, within 1 hour of finishing cooking. Refrigerate it and eat it within 24 hours. Reheat it fully until steaming hot throughout. Eat it completely after reheating. Never put it back in the refrigerator after it has been reheated once. Never leave cooked rice at room temperature for more than 2 hours. For chicken and poultry, use the oven when you can. 175 degrees Celsius, covered in foil, for 15 to 20 minutes. If you use a microwave, cut the chicken into small uniform pieces first. Use medium power, stop and rearrange halfway through, and rest it covered for 2 full minutes before eating. A food thermometer reading 75 degrees Celsius in the thickest part is the only reliable confirmation of safety. Or eat it cold, genuinely a good option. For cooked potatoes, embrace cold potato salad. It is delicious. It retains all the resistant starch benefit, and it produces none of the acrylamide concerns associated with a second high heat event. If you need them warm, low, and slow heat, steam or a covered low oven. Never refry already cooked potatoes in oil. Keep raw potatoes stored cool and dry, not in the refrigerator. None of these changes is difficult. None of them is expensive. None of them requires you to stop eating the foods you love. They are adjustments, grounded in real science, supported by real sources, and genuinely worth making. That is the only kind of health advice I have ever been interested in giving. Take care of yourself, reheat wisely, and share this with someone who cooks.